numbered by sequential number and name of the presenter. If it is not first time when you see Microsoft window, just, yeah.
Alright, so I'm going to be talking about non-adiabatic coupling of electronic states. So I guess this is the theory. That's probably going to explain it better than I will verbally. So unless anybody has any major complaints about that, I'm probably just going to move on.
You can tell a couple of words.
Okay, so I guess
your interpretation.
Yeah, so for me, when I'm thinking about non-adiabatic coupling, it's easier to think about what it is that you're ignoring when you're taking an adiabatic approximation, which basically just assumes that there's no connectedness between the electronic states and the ionic motion, or the nuclear motion, to be more specific. So whenever you're taking any non-adiabatic couplings, you're actually considering how your nuclear motion is actually moving and messing with your electronic states, and I guess, like you said earlier, ruining the orthogonality and causing different spatial overlaps in time. And I just took that equation straight out of one of the things that you sent in one of those emails. I don't know who wrote it, I guess. There wasn't the name on there.
And where are coordinates from molecular dynamics that Daniel has computed or taught us how to compute?
That would be the big R, I guess, in both cases.
And what is your time?
The T.
But
they are not in online.
Okay, probably you need to kind of coordinates here. One electronic small r and one is a big one, right?
Yeah, that notation is a little confusing.
In a way, how is it written? You take.
So I think what they're assuming is that you have all
You just overlap two Kansham orbitals at moment t and at moment t plus delta t.
Right.
But this dependence stays only on the nuclear time dependence part.
Yes. So the little r, I would imagine, is just whatever point in the space you're looking at, and then these are, the set of all of
So your electronic degrees of freedom don't change with time? They don't depend on temperature, on temperature, on time?
Oh, I see what you're saying. Yeah.
So I can do that for myself.
Well, okay, they would have a time dependence through this. I would imagine, because you could determine your electronic state based on your ionic positions, right?
Mm-hmm.
So
technically,
because you have the time dependence in there, you would then get your...
Technically, you're kind of thinking that your position of nucleus is kind of a snapshot.
Yes.
Right?
Yeah.
So it's fixed at that moment of time.
Right.
And it's not really moving because they are very slow.
Yeah.
But you're still, of course, including that your electronic degrees of freedom is still time dependent, right? And you're kind of solving this equation, which you have this delta t in the front and so on, as a dependence for electronic degrees of freedom.
Say that last part one more time for me. Something about the electronic degrees of freedom. I missed a couple words.
In other words, your r, well, your wave function dependent on a r with the index I, right?
Yep.
And the wave function dependent on a r with the index j, right? They are not orthogonal. Because otherwise, if you don't have time dependency for your r, and r is exactly the same, well, I mean, they have to be orthogonal, right?
Right.
Which means if they have different indexes, then this integral should goes to zero.
Yep.
But they are not, because technically you're taking them at different moment of time.
Right. Yeah, because we've got.
And that's why this overlap will have some values, right? Okay. But nuclear are considered like really fixed at this moment of time.
Yes. Or at least as far as I'm aware, yes.
I would put it probably backward, like your nuclear is not time dependent, but your electronic degrees of freedom should be time dependent.
Okay.
In this equation, but if you understand it, it's fine.
Yeah.
Just the way how you define it. You kind of answered it already.
Yeah. Yeah, that would probably make the notation. I'd have to think about how to write that. Okay, so after you have run your molecular dynamics, I guess you don't explicitly have to make a duplicate directory, but I would highly recommend it so that you can't mess anything up in your original molecular dynamics directory. So just make a new directory, copy everything from your MD directory into that one. If you have any files that start with a lowercase p, just get rid of those with remove p star. It shouldn't affect anything because none of the important files start with a lowercase p. And then you're going to need to edit the postcar file. Excuse me. The postcar file.
Well, before you go into postcard file,
Yep.
right? So it looks like you don't have wavecars on these directories as an output. Am I right?
Oh, it's right there.
But it's only once. But again, you run dynamics. It should be time dependent then. So your wavecard has information on each of your time scale along the trajectory? Or is just a wavecard which is taken at the very last moment of your trajectory?
I actually don't know exactly what the wavecard has. It's a binary file, so yeah. I would imagine that our car has a lot of the vital information.
You can take a look
for
on the
that
size of the wavecard. I mean,
Yeah.
just like, I should be curious about it.
Mhm.
So you can take a look on the size of the wavecard when you create it after the first step of the dynamics.
Yeah,
And if
and
the
then look
size
at it
is not
later.
increased,
Yeah.
doesn't matter was it binary or not. If the size is exactly the same after you'd run thousand or how many steps,
Right, then you're clearly
so
not
clearly it's just
size.
rewriting your wavecard at each moment of time. And I think this is what is that. What is it doing?
I think
It's
that's how
not
that
collecting information on a wave function at each moment of time because then your file would be enormously
yeah,
huge in
gargantuan.
size. It's just rewriting your wavecard at each moment of time.
Mhm.
So would you recommend to use this wavecard, save it? Is it really useful? Because you said like, oh, you have to duplicate everything from your files. What about this file?
You shouldn't explicitly need that. Well, no, you. Okay.
So
Later on, you will need a wavecard file,
So
but that will be
later
generated.
on, actually, we have to recalculate this wavecard.
Right. Yeah,
at
and
some
you need
stage.
to recalculate it every
Then
time.
the question is, why do we recalculate and why we're not using it right away? So why to do it twice? Spending time for nothing then. There should be some tricks there then.
Why are we doing what exactly twice?
Why are we not using this wavecard? Why we actually have another step to run the WASP and recalculate the wavecards when we calculate non-adiabatic couplings?
Oh, yeah, I see what you're saying. That
Or we
would
use these
actually-
wavecards.
Yeah, that seems like that should be a shortcut.
This is your
should be
after running
viable.
MD, right? So this is
Right,
just
yeah.
you. This is what kind of part which Daniel was discussing,
Mhm.
right? So you run your molecular dynamics. You got all these files.
Yeah.
Right?
Well, yeah.
And,
'cause
we
if-
not, and then you're saying you copy everything. You're renaming your postcard. I guess this would be on your next slide. But actually, you're renaming your concard probably, right? Not postcard.
Concard to postcard.
Yeah. You use concard for the next step, not postcard.
So concard has a last geometry.
Right. Yeah. It's a
And
postcard. but at the
wavecard
end.
also the wave function
Oh.
of the last step.
Postcard has your initial geometry, but you need
Yes,
concards which
but-
include all information.
I believe that we actually want the postcard and not the concard for this part.
Let's not
I would
confuse. Let's not
think-
confuse each other. Tell us first, how many slides do you have?
Like 10.
Okay, before going through the slides, give us in one word or two words approximate content of each slide.
So
And this is slide number 3?
yeah,
Number
something like
2.
that.
Number
Yeah,
2.
this is like the very beginning of what you actually do to calculate your couplings. Because this has turned into a multi-step process every time I've tried to do it. So you run molecular dynamics, then you want to create all of your like PXXX files where XXX is whatever number.
So,
added with.
okay, good.
And then?
Um,
And you will explain how you do it. But then?
Yeah, so after you have all those, I guess I wrote a script on here that I'm going to mention that if you have your molecular dynamics separated into multiple runs, because you couldn't do it all in 48 hours, which is what happened every time for me, then you need to rename hundreds of these P whatever files. So that script basically, and then I'll make a separate directory where you actually do all the coupling computations and run those
So
scripts.
about the coupling computations.
Yeah.
And what is the connection between this PXXX file and coupling computations?
the coupling computations use those PXXX files, which are essentially, they're the exact same thing as a postcard, but at whichever ionic step.
Here we
And now please tell what is the connection between PXXX files and question that Daniel was curious about.
Which
Oh
question?
crap, which question
Can
was
you
that?
rewind the question?
Yeah.
Daniel was trying to answer which information his molecular dynamics is funneled towards computation of couplings.
Yeah. So after you run molecular dynamics, you do have all of the information on where all of your nuclei are at every step in time. And so each like PXXX file is a snapshot of your system at that step in time. So we are going to explicitly make a separate file for every ionic step. And that is coming up next, I guess.
So which number of iBrion you used?
What's that?
Which number you used in iBrion keyword or molecular dynamics running?
Is that the one that tells you, or that tells it which things to compute, I guess? I think that one was 2, if I'm not mistaken. If that's the one, I always have to look at I can't, memory is not my strong suit, so I always have to just look at them on the wiki.
But returning back to my first question, so do we need or don't we need this wavecar?
This wavecar
Anyone
we do
can
not need.
We do not need.
We don't.
Well, if you rerun your molecular dynamic part, like this was like you run it like several times with interruptions. So after you've done your first, I don't know how many femtosecond, would you use this wavecar to restart your molecular dynamics? Would anyone use this wavecar to restart molecular dynamics? No? Why not?
I guess
It will save you a lot of time because anytime when you run DFT, you start with a guessing wave function. But you don't need to guess this, right? If you have this one. So if you have interruptions in molecular dynamics, and if you have a wavecar saved and created successfully,
then you might as well just throw that in the next directory.
Use it as an input file to restart it in the next directory and restart it. You save a lot of time with this. However, you cannot use this wavecar for the non-adiabatic couplings calculations.
Right.
Why?
Because this is only one step of like 1,000.
Oh, you can
So it's not really-
you can run it and resave it, right? Like save it after one femtosecond when it's created, you can call it wavecar 1, then it will be wavecar 2, and 1,000 wavecars. You can probably save them, but we don't do it. Any reason? Anyone knows why you cannot use this wavecar for calculation of the non-adiabatic couplings, or actually for calculation of just regular electronic structure calculations? Anyone knows? No? Have you been ever trying using this?
John Fogel knows.
John? I don't know, does he hear us?
It is very simple and provocative question. Most of you know the answer.
Does it have to do with like spin restriction?
We don't usually write it. That's why I never used it.
Yeah.
Any ideas?
Does it have to do with like spin restriction versus like non-collinear spin or anything like that?
It's dynamics.
So it is not the optimal geometry. Geometry is very distorted, and it's only one snapshot, so it doesn't give you a representative picture of the electronic structure. And one snapshot is not sufficient to get non-adiabatic coupling because you need a lot of points, a lot of snapshots.
And again, read the manual where they talk about adiabatic, just regular molecular adiabatic dynamics. They have a recommendation there not to use the wavecars for the electronic structure. If like you run your dynamics, then they recommend to restart, like you have your like snapshots or coordinates, restart, recalculate if you need the electronic structure, these specific snapshots. Don't use these wavecars because they are kind of projected to the new, so to speed up the calculations, the wavecar which is created at the last moment is actually having, it's not the real wavecar corresponding to the electronic structure of this moment of time. They kind of project it, they kind of guessing it as a next step due to the motion of nuclei. So it's actually not very accurate wavecar in other words. And it's done for purpose because this way how they do it, it speed up the adiabatic dynamics, but it will be not accurate for the electronic structure calculations. That's why if you need to get just wave functions for electronic structure with this specific geometry, right? You have to just do single point calculations with the saved coordinates from your previous step, right? You can probably restart your calculation again using this wavecar if you want to, but you cannot use it directly and claim that this is your.
Okay. So this would be a different wavecar than I would get on like the 1000th iteration.
When you do
of the
non-abatic
for loop in that
dynamics, when you like, you will go to this non-abatic couplings calculations, right? Because there you also restart your VASP calculations, starting with these P files, which has information on the coordinates, right?
Okay. Yeah.
So, and your settings, your postcard actually is different comparing to this adiabatic dynamics. It's just regular electronic structure calculation postcard with a single loop.
Okay.
Right? Without really motion of nuclei.
Yeah, because I definitely do single point calculations later.
Right.
Yeah, I'll ask you, I guess, something when I get to that point. Because
But again, the practical point, if you run in adiabatic dynamics, it's a good idea to probably run it for shorter time, because if you run it for thousands and then you break out, you never really create this wavecard. Maybe that's why you're not using. Because if you run it for the whole period of time, and usually you don't have enough wall time to finish it, right? So then, if it's interrupted, then you never really create your wavecard. So probably it makes sense to run it for whatever some reasonable time, like as much you can do for this specific wall time you are running for your regular calculations. Create your wavecard and then restart. Let's say you're doing 200 femtosecond, then you restart from your 200, going from 201 to whatever next 400 something. Restart it with this wavecard. Then it helps you to speed up the molecular dynamics calculations.
Okay.
But for non-abatic couplings, this wavecard are not very much useful at all.
Okay. Cool. So, so once you've made your duplicate directory and you've copied everything into it, you need to edit the postcard because some of the scripts are not written for this version of VASP. So the only thing that you need to do is just get rid of this line, because all this information is already stored here, so it's just kind of redundant anyway, I guess.
Again, return back. You use this postcard from your adiabatic dynamics calculations, right?
Yes.
So this is exactly the format which you were using for adiabatic calculation, molecular dynamics calculations?
Yes, this would be the same postcard as up here.
And again, you have to change it because now you're really not running for your kind of go in, we call it step 2, when you're really calculating non-adiabatic couplings, you restart your Gaussian, you restart your VASP, but now you're not doing dynamics anymore, you run regular electronic structure calculations. Means you just optimize self-consistently with this specific nuclear position, you self-consistently optimize the electronic wave function. And that's why you need to modify your postcard a little bit, because the formats are slightly different.
Okay. Yeah, because as
no,
far as I know,
it is needed because
this
code for
script is not written for this version of VASP.
Converting, yes.
So this script is expecting this line to not exist. And so if this line is here, you just get a bunch of blank
Then
output.
why is it here?
It is a fact of the VASP 4 and 5 only. 5 they have one extra line in postcard format.
But then why is it running for dynamics?
But this script is written for VASP 4. So it's not about calculation, it's
why
about
you have this line in your postcard for the dynamics, and it's not a problem when you run dynamics with this line in a postcard?
There is no problems at all.
Yeah,
So,
Yeah, VASP expects that line.
We do use.
Then why you need to
Wait.
delete it?
Let me talk.
For this thing.
We do use latest version of VASP, number 5,
Yes.
which has different format of saving files. But in our repository, we do have a very good script that was written for the version number 4 that no one wants to change and update. And in order to apply the script to results coming out of version 5, one needs to remove one line.
Actually, I create the postcard differently, so I just.
So you make your own
In
way.
Thunder, we have only VASP 5, so we don't have that issue.
Okay.
4 and 5.
Ah,
We have all same format.
okay, whatever.
Yeah. So when you try to run this script, if you just get a bunch of blank lines as output, it probably means that you didn't edit your postcard, so just go back, do that, and try to rerun the script. If you get all this going on as output, then that probably means it worked. Probably still a good idea to just look at one and make sure that you do actually have all the information that you need. So after you've done that, So for me, all my molecular dynamics jobs took more than one run. So I had to break these into multiple directories, and the script that I found was not working for me. It would only work in certain cases, I guess. So what you can do is in your second directory, after you've done all the same steps that I just talked about, you're going to get a bunch of, like P00
This is
to...
output? What file is it you're showing?
This is a script that I wrote.
Ah, okay.
Yeah.
But the files, the files
These-
PXXX.
Yeah, these are the PXXX files.
But
right?
how you
So,
create your PXX and so on? Where
With
did you
this
get
script.
your PXX? Huh?
you run this script, and this will give
Well,
you
well.
the PXXX.
What is your input for this script?
There isn't one.
Huh?
You don't need to give it.
Wait. This is wrong. This script doesn't need explicit input in the command line, but it
Right.
reads some
But it
files.
reads the files from
Oh, yeah,
adiabatic
yeah.
So which
dynamics.
files?
Yeah.
Which
Which
files?
files?
I thought you meant like what.
No.
user
Which
input you
files
need.
does the script read?
What do you need to run? Like, let's say if I have an empty directory and run this script, what does it tell me?
I would
And
probably
then-
just complain and say, you
Yeah,
don't have
we'll,
what you need.
we'll stop and
How-
say
how
something like,
you would
can it
complain?
read the file and gives you the name of the file?
I would imagine outcar and maybe another one.
Outcar and postcar.
Okay, yeah.
That's why you have to edit the postcard.
As an
'cause it
outcar
uses
or
that
Oh,
exdet
right,
card.
yeah, true that.
Because exdet card is easy. Exdet card has all the postcard formula.
See,
Which one you
it is
use?
named outcar to postcar.
No, I'm saying if we do that exdet card, is that wrong? I mean,
No. There is a redundant information. It is repeated in both outcar and exdatcar. They have repeated information.
Outcar has
Yeah,
everything.
so-
Xdatcar has only
but since we need
coordinates.
only a coordinate for this one, then we can just take it from exdet card.
Yeah.
That's a pretty simple in that
Yes.
case, taking from the out card.
So
But
you're
you-
going to
you
tell
run-
how you do this procedure in your talk number 7.
Not yet, I didn't-
You're number 7. Okay, we will.
I have
wait.
just a couple of lines Python code and it will get everything from the exec card.
Very
You
nice.
can do that too. That
Okay.
will make more
Cool.
easier.
Okay, it looks like we have two alternatives right now. You can get the same, like first of all, you need input files, right? And this
Yeah,
is
yeah, you got
postcard
files.
and outcar, or in as alternative, instead of outcar, you can use xdatcar. Because outcar has everything.
Right.
Energies,
Yeah,
even,
Yeah,
even
just
positions,
literally
everything, right?
Yeah.
But xdatcar has only positions. So to creating your, like the goal of using this file is to create this p dot
Yeah, the P
files,
whatever.
which will be used for non-arithmetic calculations,
Right.
right? And you either, like you have a script which working with huge big outcar file, Jabber has own script which is working with xdatcar,
Exdet card.
yeah, which has the same information but just only on coordinates, right?
Yeah.
So two alternatives, both might work, but the script which you are using probably works only with outcars. If
Yeah, no,
if,
you
Yeah.
should
if
be
you
able to-
if you use
Nothing
this
rude with that one,
this
ran on
script
next
for
card.
kind of and don't have outcar, it also will give you the error, right?
So what is inside this P001, P002 files? What is inside these files?
So they generate.
It's answer to question of Daniel, or question Daniel is interested in.
It's the exact same format as a postcard file.
But physical meaning, what exactly is saved in these
The
files?
positions of your nuclei.
Positions at each
Time step.
moment of time.
So the
yeah.
index at in the name of the file is a time step.
Right, yeah. So this is before you've done any ionic steps. This is the first ionic step, second ionic step, and so on.
And why? Let's say why not to have
Makes sense?
why not to have p dot like you have xxx? I think in your case probably 4x, right?
No, real file is
this
4. P is 3.
It's 3, okay. So why not, like if it's just 0, 1, 2, 3, 4 and so on, why not having 1, 2, 3, 4, why you need 3 decimal, kind of, why you put in zeros, right? Like at the moment 0 you have all 3 zeros, right?
I'm not putting zeros. The
You
script
don't?
does that.
Well, I understand you, so you don't do
they're-
it by hand, that's why you actually write the script.
They're padded for whatever reason.
But do you know the reason?
I
Like
don't know
why
the
to
reason.
worry about it? Any ideas? Why we have this special format for naming 000, 001,
For make it easy
002?
to process in the next one because the script, I
It's
don't
not
know, all other
easier.
languages started, numbering started with 0.
Any ideas? Anyone working with Fortran, writing codes on Fortran?
Yeah, Fortran is started with 0.
Fortran is actually very picky about the text variables. And when you read these files, because the next step is written in a Fortran for the non-arithmetic couplings, and when it's read these files, it's actually is very, very picky about this, how say, number of decimal place digits in a text format.
So it reads it as a text file and then converts it to numerical format.
Right,
If
it's expecting
if you
that
have
padding
different
to be
lengths,
there.
it will go.
However,
strange.
if instead of like you use probably the same scripts, right, as we use for running Normative couplings, but if you write your own scripts, let's say not on a Fortran but on some more advanced and more modern language, then you probably can completely redo this, this naming and don't worry about this 000 and so on.
You shouldn't explicitly need this for any real reason other than something requires it at some point down the line. I mean, anyway.
But it's doing for you so good. Now you know why it's doing it in this specific format.
Yeah. So, okay, so if you need to run molecular dynamics in more than one directory, you're going to, I guess I didn't show it here, that, it would have taken way too much space. In your second run of molecular dynamics, you're going to get P00, P001, P002, all that again, so you're going to need to shift all those, essentially. So what I did is I wrote this script, rename PXX, so that all you need to do is just give it the first input that should appear in your new directory, and it will rewrite all of the P whatever files for you. So if that script fails, like it did in this case, usually, so basically what this did is it rewrote P000 to the first index and then it quit. The issue is usually that you have some other file that's not one of the PXXX files in your directory. So just get rid of all those, try to just get new healthy P whatever files, and then rerun the script.
I don't get you. What is mean healthy P?
What's that?
What do you mean by healthy P?
Just a second.
LDP.
Am I right? Like,
I mean, you said
you break, like, to run your, like, you have, let's suppose you have 1,000 P, right? Named from 0 to 1,000.
Yep.
And you saying that, of course, you cannot, and at each moment, for each P, you have to run VASP. So you have to run VASP 1,000 times when you calculate, no, but actually twice more, because you, around 1,000 times. Along the dynamics.
+1,
+1, yes, not twice, just +1.
Actually,
So,
+2. Heating, molecular dynamics, and then 1,000 times.
Oh,
no,
yeah.
I mean, just for this
Okay,
case.
0 to 999.
But you're saying that you cannot, of course, just run it as a single job and do it 1,000 times of VASP calculations, right? So you have to break it into the pieces. And let's say you put it like from 0 to 50, from 51 to whatever, 100, 101, 150, and so on, right? This is kind of the goal. And then you rename your, like in each, like you're creating these directories for snapshot, how say, for regions, right? Or time intervals. And then if each this directory, you rename your P files so they will go from 0 to 50. So before you had from 0 to 1,000, now you have how many? 200 directories with 50 guys. And now your P is going from 0 to 50 in each directory.
Right.
This is what your script is doing?
Well,
Not
so
really.
that's the original problem. What the script does is takes, okay, so your first MD run has 0 to 50, right? Your second MD run will have 51 to 100. So what the script will do is it will, so after running this script, you're gonna have, what, like 20 directories that all have P000 through P50. So you need to go 0 to 50, 51 to 100.
Oh, it's okay. Now I understand. So you run molecular dynamics in different directories. So that's why you run in each directory. You run your script for creating this P. So now you have numbering of P in each directory is the same. But now you want to really make it from 0 to 1,000 rather than 200 times from 0 to 50.
Yeah, because if you have everything in the same directory, you're gonna end up overwriting everything, and that's just dangerous.
Is it clear or not? Why he needs it?
Actually, I was texting. Sorry.
Does it calculate overlaps of wave cars? So if your indices are mismatched, so you would be like overlapping your first step with your 100th step, possibly. So
because
that's
initially you don't have any wave car, it's guessing the wave car, so that wave car may be not 100%.
It doesn't know there's a previous run.
Yeah.
So
The script is always just going to give you 0 to however many steps.
So if you overlap 5 step, you can assume that after 5 step is correct.
Yeah.
If it fails again, let me know so I can debug the script.
I have not been able to break it other than doing stuff like this. Or I guess if you have this situation and you removed explicitly this file, it would probably also break because you have this weird jump right there. That's why I recommend just rerunning the outcar to postcar because it takes like 5 seconds. So yeah, just let me know if this doesn't work for you, if you ever need to use it. I'd be happy to debug it. Well, not happy, but I wouldn't mind.
Tolerant.
Okay, so after you have all of your PXXX files, you need to make a coupling directory. So what you want to do is copy the in-car, pot-car, and K-points from your geometry optimization. Edit your in-car so that you only do a single point calculation, otherwise you're never going to finish, and actually that would mess with your data as well. So after you've done that, you're going to need the scripts in this same directory. So these are all in the bin. You're going to need overlap.exe for sure. You're going to need whichever B script is relevant to what you're trying to do. So standard would be for spin restricted, NCL would be for non-collinear. I think there's like one or two other ones in there. And then you're going to need a script that will actually like request your processor hours. So you need to make in-car and a energy pop, or sorry, input overlap and energy pop for the overlap script. Those are just the same as they usually are.
So is it designed for Edison only?
What's it?
Is it designed only for Edison? Because you said requesting processor or something like that.
Oh, there's
There's
the same thing except Cori regular coupling, and you can just make one of these on your own if you want to from a different one.
What does it do actually?
So this isn't super clear on here, I guess. This is the Edison regular coupling one. This is the B script file. So what this will do is you tell the computer cluster, you know, what kind of job you're doing, all that, and then instead of just running VASP, you call this script, and this script is what actually runs VASP. So I guess the important things to... Oh, one thing that I forgot to mention, actually. I'm not sure exactly why, but this script only works for me on Edison. It does not work on Cori for whatever reason. I don't know why that is,
Did you
I guess.
use the pod module? That's why.
Okay, so on these files, the things that you're going to need to edit are all in the boxes, which got really mangled on the paper print-offs, I guess. So just let me know and I can email you a copy of this thing if you wanted to look at it. So in your Edison regular coupling or Cori regular coupling, you're going to request however many nodes. So right here and right here in the orange boxes, I believe, you need to make sure that those line up with however many nodes you're requesting, and I just put those right there for quick and easy reference. So right here, you just need to tell it what the first PXXX file is that you're going to manipulate, or run VASP on, I guess. And then up in here, you just need to make sure that you have the appropriate looping conditions. So if this is 0, just set this to 1. If this is like 57, set this to 58. And then just make sure that it will actually end at the appropriate time, depending on how many PXXX files you have. And I guess in this little line right here, just make sure that this is actually the file that you copied, and you know you're modifying right here. Otherwise, this isn't going to work. So after you've done that, just copy all of the PXXX files into your coupling directory, and then just run sbatch on your Edison regular coupling or Cori regular coupling, whatever it is that, whatever file it is that you have there. Just make sure that you run sbatch on that file. And that's it. Then you have coupling.
That's it?
Yeah.
Last slide? Okay, let's thank London. Okay, let's go one slide back. So please point your laser pointer on the near the orange box, overlap exe, lower, one line lower, here.
Yes.
So tell us more, just your vision, your interpretation, what this code does.
The overlap.exe?
Yes. Yes.
I guess it makes these OS strength files, so it actually does the computation of your couplings.
So what is the input and what is the output for this code? Even if it is not explicitly mentioned, but what it reads from file and what it writes into file.
It takes your electronic states from your wave car.
How many wave cars?
2 at a time. So like 0 and 1, 1 and 2, 2 and 3, the 2 adjacent time steps. At least I would think. And then it basically calculates this using...
So this overlap .exe implements this equation?
Yes.
For a given time step?
Right.
And your phi at time t is wave car?
Yes.
And your phi at t plus delta t is wave car new? Or whatever? Wave car and wave car old.
Yeah.
Okay. And which file can you go to the equation?
Oh, yeah.
So this v sub ij.
Yep.
In which file this v is saved?
That would be... Let's see.
Next line.
Should be
The
in
next
the
line after
OS
this.
strength.
And if you think longer?
For master equation.
If you think even longer?
Coupling.
Yes. So it should be matrix like with orbital indices skipped, like square matrix from first to last orbital, or from first active to last active orbital. Okay.
Yep.
And then in your script there should be renaming of the coupling into coupling with time index, right?
Right.
MV
So
coupling,
it moves
coupling,
it to whatever your
period.
added new decimal is.
Okay.
I was wondering why is moving coupling to coupling.
No, there is a red,
It's
red
these
font which is
colors
not.
don't show up
Oh,
super well
okay.
in here.
Yeah, definitely.
Is it better?
Yes, it is.
Okay.
Oh, yeah, you also don't need to have this one with the initial zeros, because the printf statement handles that for you, so, yeah.
More questions to London? Daniel? You are the target audience for this talk. It's your chance to ask.
I understood most of it, but the part,
Next week you repeat everything.
yeah, the only thing that got a little overwhelming was whenever you had all those P1000 files. How many files did you have right there? Yeah.
Oh, yeah, when it's all said and done, you should have, well, for me anyway, I'm doing 1,000 steps, so yeah, you got like 0 to 999. So it's just a lot, and then this script actually makes a file for every intermittent step, I guess, for an OS strength, for master equation, for coupling. So after you run it, this directory gets massive. Because you have like 4 files for every one of these steps now.
Jagat, you wanted to ask something?
What is the webcar world you just mentioned? Where did you get from?
The wave car?
Webcar world.
Oh.
I saw it now. Webcar and webcar world.
So, okay, so you basically just run VASP on the first PXXX file that you have, and then when you go through in the loop, you just add 1 to that. You move that old wavecar to wavecar old, and then you're going to rerun VASP, except at the next ionic step, I guess, using the next postcard. So then after you do that, you're going to have wavecar again, and then when you repeat this loop, you're going to end up replacing that with wavecar old. So you keep rerunning VASP over and over and over again, so you get new wave cards every time.
Okay, if I ask what is the necessity of doing the webcar world from the previous step?
The first one here?
I mean, why are you using one webcar from the previous step?
Oh, because that has
No, previous means the previous time step in the loop.
Yeah, so the wavecar old would have this information in it, and then wavecar has this information.
More questions? If not, let's thank London.
That was just a quick one. How do you know how many I's and J's you have for your couplings?
You specify that.
In which file?
Input overlap, and your energy pop, I guess, too.
Yeah.
But yeah, these are, they range from there to there.
Yeah. Thanks for pointing on this. Okay. Thanks, London, for one more time. Now, one person will appear at the stage twice. So it is Aaron Fordy, who will first give brief introduction on the correlation functions, and then he will have a break and then he will tell about electrodynamics.
So usually go through these presentations, we usually jump from making couplings to RRR files, but there's usually one more step in between, and that's making correlation functions.
There was slide advancer.
Oh, right here.
Okay. Escape.
Oh, okay, so just very brief technical details. So I didn't know what a correlation function was until like a year ago, so I assume like a lot of undergraduates might not know. So basically it's just a measure of how similar a quantity is in space and time over different time periods. So like if you have one function at time t and you have another function at t plus like a dt, and it just measures like how similar they are at different times. And they don't have to be different. These can be like f and f, and that would be an auto correlation function. That's usually what we do. And so the big deal is we use autocorrelation functions because rates of electronic transitions you can use those to, or you can use correlation functions to determine rates. So this guy's a rate, and then this guy here is a fancy way for autocorrelation. Essentially, like if you go through a textbook and read it, all this contains like information from Fermi's golden rule. So it's just another way to write Fermi's golden rule. So that's why we have.
What's the difference between correlation and autocorrelation?
Autocorrelation is how it measures its similarity with itself in time or space, and a correlation function necessarily doesn't have to be with itself. It can be with another function.
So if we change it to G here, it will be autocorrelation.
Yes.
And would you agree or disagree that there should be some exponential with time?
I won't disagree. Okay. So yeah. So and then this is just a nice way to visualize what an autocorrelation function does. So this first plot is just a plot of an autocorrelation of a wave pulse. So how do I?
Oh,
it's still on the marker.
To draw?
Yeah, it's still on the marker.
Okay.
There we go. So this is the plot of an autocorrelation function, and then let it go a little bit. So these are two wave pulses. So at t0 they're on top of each other. So you start out initially at 1, and as you go through time, the wave pulses go out of phase. So you get negative correlations because you're multiplying a positive and a negative number. So you get a negative number. Go through again. They come back into phase a little bit. So you get a positive number again. They go back out of phase. Then after some time, they don't know each other anymore. Then if you plotted those...
So your autocorrelation is, correlation is red times blue and integrate over the whole space.
So yeah, you basically just add it up at each time step.
Okay.
And then keep going. Then yeah. So if you plotted the values of the integrals at each point, it would do something like this. So this is in phase, out of phase, somewhat back in phase, and then this, they have no idea they're next to each other anymore.
Nice.
And so to make autocorrelation functions from the wavecars that we use, so the MATLAB code is pretty standard. It hasn't changed at all since I've been here. Correlation v3h, and you have to give it coupling, or all the coupling files that you generated. And then you just need energy pop, and you may need overlap, you may not, I can't remember, but I just usually put it in there anyway, because you need it eventually. So you feed it in these files, and it outputs some correlation functions of orbitals with each other, and basically takes all those correlation functions and converts it into an RRR. And to run the code, it's pretty robust. Basically all you have to input is some specifics about about the orbitals that you're using. So you enter your HOMO, max and min from your input overlap, and sometimes you just have to change like these loops just to load in the coupling files, depending on how many you have. So if you have 1,000, there's another loop below this that goes up to 1,000. And if you have less than 1,000, you just have to tell it which number, or else it'll yell at you. And so if you run the script and it runs pretty healthy, this is a pretty typical figure. So it starts out at 1, decays very quickly, and then kind of oscillates. And then each of these colors are one of those core underscore homo files. So these are just correlations of or autocorrelation of orbitals. Ones near the gap anyway, which are usually the important ones we look at. And that should be it.
So can you go back to the first slide? Let's thank Aaron just in case. And, if we remember presentations, well, some of us made presentations, remember presentations by Levi on dephasing, especially Javid should remember it. Their autocorrelation functions were decaying much slower. So what's were the dephasing autocorrelation functions presented by Levi and autocorrelation functions presented by Aaron applied to the same type of functions or to different characteristics?
So I've always assumed that dephasing was between different pairs of orbitals. So yes. I know for Redfield tensors anyways, they have I, J, K, L. So dephasing would be like the time that I and J are dissimilar from K and L.
Which function, autocorrelation of which function are you showing here?
So you say the black one is like homo and homo minus 1.
Autocorrelation of non-adiabatic coupling.
Yes.
Your couplings file.
Yes.
Okay, and Levi and several other people, dephasing were applied to energy of orbital. So not the coupling, not the transition, but just energy of orbital, how it slowly changes in time. And autocorrelation between orbitals, and correlation between couplings behave on very different time scales. Okay. For orbitals, it lives for like 10, 20, maybe 50 femtoseconds. For couplings, so the main feature in this figure is that everything drops rapidly within 1 or 2 femtoseconds. So there is no correlation. The couplings, as Aaron defined, do not know about each other after a couple of femtoseconds. So the system has no memory.
So I'm just wondering isn't it better to look on the fast Fourier frequency rather than looking on the autocorrelation functions?
Well,
it will be white noise.
Then, but you can see the frequency, how is the overlapping, is the same frequency or different frequency. But in this case, what is the quantitative result from these autocorrelation functions?
Well, mostly this quantity here is what we're interested in.
How can you interpret this, what's the word, vibration, quantitatively?
So you can see initially at some time it decays really quickly, and then over time they kind of come back into phase with each other. But if you run this long enough or you get good enough statistics, over time they should average out to 0. So like this is just like, view it as statistical noise.
The reason for these oscillations is accumulation of electronic phase, and electronic phase accumulates really quickly on like attoseconds. So if one would redo this figure on the fraction of femtosecond, like doing it from 0 to 1 femtosecond with 1,000 steps, one would see continuous function with slow decay and maybe analyze it somehow. But this ultra short time ranges are not yet in our focus for practical applications. If one would model the free electron X-ray laser for sub-femtosecond processes, one would do modeling on the really short time steps.
But if we take FFT of this autocorrelation function, FFT, I mean fast Fourier transform of these autocorrelation functions, which one would be more convenient to read this information? This one or of FFT?
Which information?
I mean, for us looking on how many different frequencies involved on these things.
Unless you can visualize Fourier transforms in your head. Like, you probably couldn't do it from this, but I mean, you can.
In order to do Fourier transform, you need to shorten the time step 100 to 1,000 times. At this resolution, it is almost like a noise.
Okay.
So the only importance is the absolute value of couplings when they are laboring in time.
Any other questions?
More questions to Aaron? If not, let's thank him once again. And according to the schedule, we have presenter number 4, Dr. Fatima. So she will tell the practical steps, how to, she will focus on more details on how to convert this set of coupling files into the matrix of rates which will be used to propagate electronic state. Is there a slide advancer with laser? Okay, good.
So I'm going to talk about how to convert non-additive coupling files to ordered field tensor. This is the theoretical method. On the fly non-adiabatic couplings are computed using this equation. Here we can see 2 K points, 2 different set of K points, but the rest of the equations I used only 1 K point because for red field tensor calculations I used the code for momentum constant system. So here in this case K equals uppercase K equals lowercase K. And the second equation, this one is autocorrelation function, and the Fourier transform of this autocorrelation function is the transition rate, and these transition rates are the components for calculating red field tensors. So in order to calculate red field tensor, we need all the coupling files, a couple of 100 files. So, and energy pop file, and the energy pop file should contains energies of states, which energies of states that are we interested to calculate. Energies of states, those are used to calculate for coupling files. Actually, import order file. Suppose if I have 700 states, 150 states, and if I am interested to suppose 30 states lower the HOMO and 30 states above the HOMO, 30 states below the HOMO and 30 states above the LOMO. So those states, this energy file should contain the energies of those interstate states. And another file we need, that correlation MATLAB code. Here is the code. So we need to modify a couple of values here. The HOMO, the state number of HOMO, and a maximum minimum state, maximum state, and number of coupling files. Here we can see 3 for loops. This one for just 1 digit, this one for 2 digits, and this one for 3 digits. Since I had 700 something files. And then you need to put all these files to MATLAB directory in your local computer, and then run the correlation code. Then you should get this RR file and this PDF file, and you can modify this code for plotting the rate-free tensor.
Okay, let's thank Fatima. Daniel has a question.
I'm sorry, I still don't understand what I see whenever I see those types of diagrams. What is it telling us exactly?
Here we can see the states, 10 states below HOMO and 10 states above or LOMO. We can see the probability of population transfer. Okay, so suppose for I indices we have suppose 60 orbitals, and for J 60 orbitals. So here we can see how the electron can transfer. We can see that electron can transfer to the adjacent state since the off diagonals are 0. Suppose for this bar, this is HOMO -4, I guess, and this is also HOMO -4. So they are the population transfer to the adjacent states.
So probably it's HOMO -5 to HOMO -4.
Yeah, ±1.
Yeah.
Not like from electron cannot transfer from like HOMO -5 to suppose HOMO -10.
Well, it can, but the rate of such is very low by several orders of magnitude.
Yeah, and this bar is the probability. How
So the
high
bigger
the
the bars,
probability is.
the faster it goes.
The probability is
Okay.
high.
More questions to Fatima? If not, let's thank her once again. And after a little break, we have the same person on stage. Thank you for volunteering twice. So right now, London and Daniel may establish practical questions. Suppose we do have this RRR file with rates of transitions, but we do need occupations of orbitals as function of time, and maybe average energy of electronic system to see how the energy dissipates in lattice vibrations, how charge transfer happens, like what to do with this RRR file, with this set of rates.
Yeah, so this is just getting results from our dynamics, so it doesn't go in depth how it exactly computes the rates for all these, but it's just showing where the relevant parameters are that you need to change to generate the figures to analyze later. So the needed files that you need is, so there are a lot of dynamic script names floating around, but this is usually the most reliable starting point to start with, is this one. And then usually if there are changes, there's additions after the 3. So depending on what you use.
So what does it mean HSP at the end?
I don't know, I've always thought about it, but nothing quick came to mind, so.
Maybe you won't remember.
Yeah, because previously she was a group member at USD. So I guess she modified this code.
So it's abbreviation of the name Huang Shuping.
Yeah.
Oh, okay. I have seen that name.
Okay.
And then this must have been his 3rd attempt.
Probably.
So if you modify the script, just add your initials after.
If you discover an error, it'll be your name, named after you. So yeah, so this is the general script to use for dynamics, and then you just have to feed in a couple of files, so input overlap, energy pop like normal, so then the last two talks talked about how to make RRR, so we feed that into the dynamic script. And then for visualization, sometimes you want the band out. That would be for like standard VAST calculations, and then there's also been an update that Dimitri has been working on for spin orbit coupling band outs. And that's not in this script, that's a different one. So if you do need that at some time, you can contact one of us, we can take it out from somewhere.
Can you briefly, in like one sentence, summarize what is standard band out, and how does it relate to main interest of London, charge transfer?
So band out basically just takes power charges, which are written as 3D in space, and it just compresses them into 2D, and usually,
or maybe 1D.
Or yes, it's 1D. So it projects them along X and Y, and then we can see along Z. So usually, whenever we make models, if we want to look at stuff like landedness for charge transfer, you have your hole and acceptor and donator along Z. So
and band out is just one file that summarizes all orbitals together.
Yes. So it reads in all the par charges corresponding to your energy pop or input overlap. And band out, there's a Perl script somewhere in the bin. And then for these, there's a MATLAB code that you have to use to generate this.
So one of the band integrate scripts generate this band out. And if you want to inspect the transfer of charge carriers, you will need to create this file. You just skip it right now to be short and fit in time.
Yeah, so then you feed in these files, and then the outputs that you get if it runs healthy is energy relaxation, and for your average energy of your carriers, and then where they go in space as they relax, which is from the band outs, and then it also computes rates of relaxation from your initial conditions to the band edges. So when you first load up the script, this is what it looks like to begin with. So you have I, H, and IE. So those are just your initial conditions that you choose for your hole and your electron. And I forgot to mention in this, but 1 in both these cases is HOMO and LUMO. So if you wanted to do HOMO minus 20 to LUMO plus 20, it would be 20, 21, and 21. So whatever your LUMO plus Y is, you just add 1 to that for IH and IE. So, and then, well, in principle, you could just do a bunch of random numbers and put them in there, but just to save time, good numbers to do would be orbitals from your oscillator string, so most intense transitions or transitions that you're interested in looking in. So that depends on your system, and just something you have to know as you're processing the data. And then some parameters that you have to change depending on the system, so Z steps and Z size. So Z size is from your postcard, so the size of the Z dimension. And then Z steps corresponds to your band out, so it's the number of like grid points along the Z axis, so your resolution basically. And you get that from band out, so whatever the size of that is. And just a couple other things you have to input to your HOMO, and then Omin and Omax from your energy pop file. And then a couple other parameters you can play with. So there's time steps, so that's basically your resolution and time, so how many like increments it does. So I don't know, I've never had to mess with it too much, but depending on how fine a data you want, you can increase this by just increases the runtime of your simulation. And you might get small variations in your rates just because, well, if you don't run as many steps, you're in coarse grain, so you might miss some transitions. So the higher that you increase time steps, probably the more accurate your results are going to be. So you can play with that until your rates are pretty consistent, and then optimize it that way. And then, so that's number of grid points in time, and then you can also change the length of your dynamics in time. So generally, stuff we're interested in occurs on the nanosecond time scale, and that's what this is set up for at the moment. But if you wanted to increase, like say you wanted to go to millisecond for some crazy relaxation, so he would just increase this until, well, I put a halt in a strategic place and just keep increasing the number until it goes to where I want. But you can figure out other convenient ways to change this number too. So changing this box number increases the time of the simulation. And then those are really the only other two parameters worth messing with in the program. And then if it runs healthy, so this will pop out at the bottom, KE and KH are your rates of the electron relaxes to the band edge, which in this case should be NA. Like these don't correspond with each other. And then K hole would be the time it goes from here to here. So if you do have like 2 multi-relaxation steps, like it won't give you one for each. You have to do some extra legwork to be able to get those transitions. So you get rates, you get these pretty figures. So this is relaxation in energy space. And then this would be for a band out from like a standard calculation. So blue is your hole. So you can see at the time the hole goes up, the electron stays down. So that indicates you have a charge transfer that occurs in your simulation. So that should be it.
Okay, let's thank her. Any questions? Can you go to the last slide? If I would see it for the first time, I would be able to follow interpretation of the first green figure, where your y-axis is probably energy.
Yeah, so when you run these, there are labels on them, but I usually cut them off when I post-process them. So yeah, I would say this is energy, this is log time.
Okay, and for the second green figure, what is y-axis?
So this would be like your z size.
So it's Cartesian, it's z coordinate.
Yeah. So this looks like, I don't know, 15, so 30.
In angstrom?
Yes.
Okay.
So basically the z component of your postcard is what it should be. And then the x-axis is again log time.
And green means that electron and hole are approximately in the same space region, or they compensate each other. But if it splits onto blue and orange, it means there is some charge transfer.
Yes, that's what it indicates anyway. Usually you want to take like a VMD of your model, just kind of place it so it looks roughly the same, so you know for sure that it's charge transfer.
Okay. More, okay, David?
How did you calculate the relaxation rates?
So, well, that was one of the prefaces for this presentation. I wasn't going to talk about how the code does it, but basically it just, so it takes all the input orbitals and it produces like a superposition based on your initial condition, and then it does a time step, takes the RR file, computes relaxation from, like, if you're at LUMO plus 20, and they would calculate the rates of relaxation to all the orbitals below it,
Up to
or
frontier
possibly
orbital.
above it.
I mean, up to LUMO, frontier orbital.
Right, and then it just does that each time step. So it's a average relaxation rate. So at each time step, it doesn't compute a new rate. So it's the same rate throughout this whole simulation.
So you calculate relaxation every time step, and then.
Yeah, so you give an initial population, or do you want to say something?
Oh, no, complete your explanation and then I'll intervene.
So the way I understand is you tell your initial population. So you do a time step, tells the RRR tells it where to send the population, does that again. So then you have like maybe 3 bands that are populated a little bit, and then RRR tells population from those where to go. And then you just kind of get a steady, well, usually you get like a steady waterfall of population of your bands.
But that population is not maybe initial population is maybe 1, final one maybe 1, but intermediate is that 1, or is like
It's
fraction of
Fraction, because it is distributed between several
distributed
orbitals.
so the sum should be 1.
Yeah.
So if we repeat same activity next year, maybe waterfall picture would be helpful to understand what is going on.
Yeah, I thought to put it in, but I guess I just didn't. So
Just to keep addressing question of Jabet, what are the dashes and solid line, and how are they related to the rates of transfer or relaxation?
So those are energy expectation values for each. So dash just for electron, and then solid is energy expectation value for holes. And so based on those, you can calculate relaxation rates.
In that case, rate is changing with the time, right?
Yep, but you can fit it to different functions, starting from the simplest mono exponential, but you can also try to select more complicated fitting function.
And we assume single exponential, well, for regular, like from this code.
But in this case, seems like your whole relaxation rate is not a single exponential.
Right, but basically what it calculates, it takes the time from here to here, it just takes the inverse of it. So you have this relaxation from here to here, but you don't have any information about the intermediate.
Then how about the electron relaxation rate? Because it seems like it stayed on the same energy over time.
Yeah, it doesn't. So the initial population was LUMO, that's what the initial condition was. So then it's already at LUMO.
So
so there's no relaxation.
Energy relaxation rate for electron is not reasonable in this example.
Right, because it's
1.63 seems like is
or maybe you started from LUMO plus 1, something like very close in energy.
I think this figure I was trying to do a waterfall for this image, so I didn't care about the electron. So this should be like if you're doing like a real calculation, like from an optical transition, like this would be up here. Relax now. This is not something we would publish.
More questions to Aaron? Daniel? London? Okay, let's thank Aaron once again. And we have 2 talks for the next 15 minutes. Number 6 is by Dr. Han, is about how to convert the outcome of quantum dynamics into some observables related to experiment. So Aaron already told how to assess the rate of energy dissipation and how to visualize the dynamics of charge transfer. But there are also important processes of photoluminescence related to relaxation energy. And right now we will hear quickly how can it be assessed.
Yeah, so to calculate the photoluminescence spectrum, we need 5 input files. So the RR energy bulb and also bandoffs are the same as the one mentioned by Aaron. So I guess the special code is this code. And also we need this for master EQ. So this is just oscillator stress in matrix format. So here, how can we get the for master EQ? So basically we find this information from geometry optimized model, and then we can just run this code, and then we end up with for master EQ. This is how it looks like.
Excuse me. What is the dimension of this matrix? I mean, which dimension is what is?
I guess this is just
number of orbitals times number of orbitals. It's square matrix. But if you use not all orbitals but a window, active window, then it will be number of orbitals in active window squared. Look, if you see symbols, the diagonal is 0 because there are no optical transitions from orbital to itself.
This is just standard procedure, so we need to transfer these files to a local PC and just run the code. So I guess the code is basically the same as the one mentioned by Aaron. I guess there is some small fraction added. So I guess you do not need to modify it. The only input you need to modify is just the initial conditions. So if the code is running successfully, then you can get this kind of figure. So this is the time resolved emission. So at each time step, we can see the emission. And this is time integrated emission. So it is taking the average of integration. And the final figure you can get is time resolved exciton picture. So, for example, if you have initial condition from LUMO minus x to LUMO plus x, from LUMO plus x to HOMO minus x. So as time goes by, finally you will have transition from LUMO to HOMO.
So the probability of excitation for excitation at given energy to exist at given time.
Right. So it's just an electron hole pair.
So 0 would be like the energy of your HOMO orbital?
No, this is the energy difference.
Oh, between the occupied.
Yes.
Okay.
Okay, this is my final one.
Okay, thank you. Any questions?
So I guess the color changes. What does that mean? It's like I guess it starts off red, then it goes yellow, green, blue, to back to yellow to red. What does that mean necessarily?
So blue means there is no emission, and red means the emission is very intense.
Okay.
So it relates to our discussion with geometry. Blue means 0, red means 1, and if it is in between, it will rainbow colors. But if at the given time there is more than one electron hole pairs occupied, their probability is less than 1, and it is smeared between them. So their absolute value is less than 1, and therefore colors are like greenish or something exotic.
So one thing, what is the lifetime of this thing? I mean, these calculations, it seems like it's too long, isn't it? It has started relaxing after 100 picosecond. And then went to the HOMO like 10,000 picosecond.
So
I mean, is it real calculation or for example only?
This is the real case. I guess this is has a very long lifetime because this is for the less than ions. This is for less than ions in sodium neutral fluoride.
Okay.
how does it correspond to experimental lifetimes? Is it shorter or longer, or?
I cannot remember, but I guess we underestimate the lifetime.
So subgaps, it is very specific experimental system, dielectric with single ion, and there are very big subgaps, which take a long time to overcome. More questions to Yun?
I have a question. So if we call this oscillation dipole a script, then we should get oscillator strength, right? And this Formaster equation also.
Yep. So question?
Like if we call this script oscillation dipole script, so we should get oscillation strength as well. Like if I suppose if I want to calculate this spectrum,
Answer is yes.
then I can see there is a Formaster equation also.
Huh?
We can see there is a Formaster equation, Formaster equation file also. We can use that one for photoluminescence calculation.
Yes. So oscillator strengths and this Formaster equation contain the same information, but it is stored in different formats. If you allow, I will answer. So when you're looking onto oscillator strengths file, it writes data in
for the dynamics
form
That's
of
what it means. So it's that's why it's saying that.
like number, HOMO, LUMO, oscillator strengths, energy like 3 electron
Called like
volts.
master equations.
And then it continues data with only one oscillator strength in each line. But if you're looking in this for master optics, it is a square matrix, and the transition between HOMO and LUMO will be just one element, where all orbitals are indexed on the rows and columns. So main diagonal exists of zeros, and one of this sub-diagonal element would correspond to homo to lower transitions. So it's denser form of to store information.
Okay, I have another question.
Please.
So for my, I believe Yulon doesn't know it.
Huh?
So I have a question for you. So for my model, I have 4 different K points. So I need to calculate that spectrum, UV spectrum for 4 different K points. So how to calculate photoluminescence? Then we need to modify the code.
If you believe, if you assume that there is no indirect optical transitions, which could be right, then you still need the 4 master equation files for indirect transitions, but you can fill them with zeros. But still, it should be same format as your 5 times R. Like R for non-radiative, and I don't know how you would call it, 4 master equation.
4Q.
Yes, yes.
It's not about this one, but I mean, it's a question after listening your answer. So what is the means of optical indirect transition? Is it possible to indirect transition, optical transitions?
No, only if you design photons that have change of momentum.
Yeah, that's I'm just wondering. So that means they have no optical indirect transition, obviously, in a real system.
I haven't seen that.
Okay.
Maybe they exist.
No, I'm just asking. And so yeah.
It's good approximation to assume that there are no such transitions.
It is also true for real
On
systems.
very short time, there could be virtual processes with that violate some conservation laws, but in overall,
Yeah, no.
more questions to you? If not, thank you once again. And last but not least, presentation number 7.